Module 3 is about inferencing of population proportions. So we are going to talk about one population study, two population comparisons, and more than two population comparisons. So what is the learning outcome is to understand what proportion is. Before this, we have learned about population means. We have learned how we can figure out the population means from the sample means. When we use sample means, we wouldn't have 100% confidence that that it represents the population means. That's why there is a confidence level wherever we use sample to determine the means. That was in chapter 2. And chapter 1, we have talked about distribution. Population can normally be assumed to follow certain distribution. A very popular distribution that we have learned is normal distribution. Apart from normal distribution, the other two important distributions are binomial for discrete problems and Poisson for rate of events. Yeah, for rate of events, we use Poisson. Anything that is to do with calendar, time, we use Poisson. Today, we shall look at another concept, which is proportion. So what is proportion? Keep that in mind. You look at proportion, not means anymore. So what is proportion? Proportion is the fraction of individuals in the population that have a particular characteristic. This is a big word, particular characteristic. It can be anything that we define. Yeah. For example, in the project, we are looking at the Titanic data set, right? So we have seen that what are the means of the age of the victims, the means of the age of the survivors. But that is means. But what about proportion? Example of proportion is the proportion of passengers who survived the Titanic disaster. Is it 50%? Is it 30%? Or is it 90%? So that is proportion. So what is population proportion? It is the share of population that belongs to a category. So we will have part of the data that does not fall under the category and part of the data that falls under the category. Right? So moving on, we are going to look at confidence level and remaining probability, because these two estimates are very important measure of how confident we are that the proportion from the sample represents the proportion from the population. This is a very important concept. You see, the word population refers to all the objects, all the experimental objects that we are studying. Population, all the actual experimental objects. Usually, population size will be quite huge. Therefore, when we carry out experiment, usually we will try not to capture all the objects and their values in the whole population. What we do, we are just going to sample. We're just going to take a fraction from the whole population. All right. Because of that, we need some confidence that the sample actually represents the population sufficiently. Right. So if our sample normally, according to the central theorem of distribution, normally if the size of the sample is big, it will become closer to the actual population. That means the bigger the sample size, the better. The bigger the sample size, the better. But having bigger size is not sufficient. We also need to tell how confident we are that this sample size is representing the population. That's where the word confidence level comes from. So let us investigate deeper what is confidence level. Yeah. Confidence level is usually expressed in numbers. It can be 100%. I'm 100% sure. I'm 95% sure. I'm 90% sure. Yeah. So in statistics, usually 95% confidence is considered good enough. Yeah. 95% confidence level is considered good enough and acceptable. So we can use it to accept a hypothesis. 95, not only 100%, 95% is enough to accept a hypothesis. So in decimal format, it will be 0.95. Now, 100% minus 95% is 5%, right? Or equivalent to 1 minus 0.95. That will give us the remaining probability. Look at point 2a, remaining probability. So if we want 95% confidence, the remaining probability will be 5% or 0.05. So this remaining probability is usually given by the symbol, the Greek symbol alpha. Yeah, Greek symbol alpha. Remaining probability, or sometimes we call it significance. So you see a lot of times in most of the formula used in statistics, they will use alpha uh, uh, to indicate significance. So what is significance? It's 1 minus confidence level. The other name of significance is remaining probability. Okay. And then one more thing you need to know is since we assume, as for now, we assume the samples that we are studying is following the standard normal distribution. It's following the normal distribution. Yeah. So therefore, every time we do analysis, we compare against the normal distribution because we assume that the sample we're studying is definitely normal. So what do we mean practically when we say data is normal? When we say data is normal, we can use the normal table, yeah, as the framework or as the foundation to determine the mean, the standard deviation, the confidence level of the sample that we're studying, right? And then for proportions, right? For proportions, we'll be looking at confidence intervals. Proportion, because proportion is part of the whole thing, right? It's fraction of the whole thing. So we'll be looking at confidence intervals. So what is confidence intervals? Okay, graphically, if you look at this chart, what distribution is this? It is a normal distribution, right? It looks like a bell curve. Yeah. Along the x-axis, will be the standard z value, and then the y-axis, yeah, the y-axis will be the what we call likelihood. Yeah, likelihood 0.00 and above. Okay. Likelihood span from 0%, 0 to 1, from 0 to 100%. Yeah, so you see, that's why you have decimal 0.1, 0.2, 3, 4, 5, 6, up to 1.0. All right. Now, look at this. Recall that I mentioned before, probability refer to the area underneath the bell curve. So the area, if you calculate the whole area, the value will be 1.0. Yeah. Let me erase this. 1.0. The whole area here is 1.0. All right. Now take a look at this. Right in the center here, the value is 0. Therefore, the line that is above the 0 is actually cutting the normal curve into two similar halves, very symmetrical. All right. Okay, so to the left, the probability to the left is half of 1.0, which is 0.5. The probability to the right is another 0.5. Now, what is the value, z value at the bottom here? Now, if you remember from the previous lecture, if you want to figure out the z value, you take the sample mean. Then you take the sample mean minus the population mean divided by the standard deviation. Okay, divided by standard deviation. So this will give you the value along the x-axis. So this will also ensure that the mean is standardized at 0. And then the z value at the bottom will be from -4 or -3 Just a moment. Let me use my stylus. Okay, that will make sure that underneath the z value, you have standard deviation 1, standard deviation 2, oh, just one moment, sorry. Hold on. My stylus is defective. Hold on. Where's the stylus now? Just one moment. Okay, so at the bottom here, you see, it will be 0, and then there'll be 1 for first standard deviation, 2 for the second standard deviation, 3 for the third standard deviation, and usually 4 is not in the picture because it's exceeding already. And then to the left of the 0, yeah, which is mean, the standard mean, we have a -1, then we have -2, then we have -3, yeah. Usually we don't show -4, yeah, because from standard deviation -3 up to standard deviation +3, it will have covered 99. It will have covered 99.7%. Sorry. Okay, hold on. You have covered 99.7% of the graph below. Okay. And then look at here. Look at here. Do you notice the shaded blue patch? The shaded blue patch. Okay. The shaded blue patch is the significance level. Significance level. Let's say if our significance level is 0.05, yeah, then we have to separate the 0.05 to these two parts, right? Which becomes 0.025. Okay, so let me show you. So you have a 0.05. What's the problem, huh? Use the stylus, so difficult to use. Sorry, I'm trying to use my stylus actually, but my stylus has been giving me a lot of problem. Sorry, so on. If I have a whiteboard, it'd be easier to do. Mm. Let me use my mouse instead. So yeah, I have 0.05 as the confidence level. So we split it to two half. It becomes 0.025. Now, may I have your attention on this idea? See, now, don't you see now? Don't you see now? Actually, there are two parts. There are two parts in this graph. Part that is not shaded, which stands for 99%. Yeah, and then 95%. Sorry, maybe 94%. The unshaded part is 94%, and then 95%, and then the shaded part is 5%. So 2.5% on the left, 2.5% on the right. So here in the center is 95%. Okay. Now, so there are two parts, right? One is not shaded, which is 95%, and then the shaded part, which is the other 5%. Now, remember or not proportion? Remember or not I mentioned about proportion? Proportion is made up of it's made up of two categories, right? Either it belongs to the category or it does not belong to the category. So we want the proportion to be under the unshaded part here. We want the proportion to be under the unshaded part here. All right. So how do we know that the value we are choosing is falling under the 95%? Therefore, we need to find the boundary here. See the boundary I'm circling. Yeah. So this is what we mean by confidence interval, lower and upper bounds. Yeah. So in this example, the lower bound is negative 1.96, and then the upper bound is 1.96. So and the value between negative 1.96 and 1.96, anything that fall under this value is in the 95% confidence. 95% confidence. We are sure that the proportion is right. Yeah. Okay. Let's say if it is not within this, then we know the proportion is not accurate. The remaining probabilities. So that's why it is mentioned at point number 1. Confidence intervals, lower and upper bounds, are used to estimate the population proportions. Next, I want to talk about critical Z value. You want to decide whether the sample proportion is representing the actual population proportion. Remember the keyword, one is sample, one is population. Sample proportion, population proportion. Whether sample represents the population proportion or not, we need to find out the critical Z value. So critical Z value is used for comparison with the value that we want to study. Okay. Let's look at so what is the critical value? The critical value, you see at the in the first chart, the critical Z value is the lower bound and the upper bound, negative 1.64 up to 1.64. This is the critical value. Okay, let's look at the second graph. 1.96, negative 1.96 and 1.96. This is the critical value for the second graph. And then the third graph, the critical values are negative 2.58 and 2.58. Okay? how come the values are different? The values are different because you see, we are using different confidence level. We are using different confidence level. For the first graph, the confidence level is 90%. That means the significance is 0.1 or 10%. So 10% we divide 2 is 5%, right? So in this graph, 5% on the left and 5% on the right. You see, 0.05, 0.05 on the left and right tails. We call this tails, yeah, on the left and right tails of the normal, right? So the second graph, the difference is that we are using more confidence. We are using more confidence, so the tail is getting smaller. You see, only the total of both tails is 5%. If we split into 2.5% each, left tail and right tail. And then for the last graph here, the confidence level that we're looking for is 99%. Okay, 99%. So therefore, the tail is smaller. You see, the tail is 0.01. We divide by 2. Yeah. Okay, so now we know what are the critical Z values. Critical Z values are the value on the x-axis that actually become the lower bound and upper bound of the population proportion. The goal is to have a maximum confidence. So if you want to have maximum confidence, right? Then your critical Z value will become bigger, right? You see if like for example, you see 2.58 versus 196 versus 1.64. So there is less room for uncertainty. You want to have less room for uncertainty. So you want to increase the this area. Yeah? You want to increase this area in the center. Now, how do we determine the critical value? Because the critical value is important. Significance, we decide how confident we want it to be. If we want to have high confidence, then the alpha or significance becomes smaller. So we decide, yeah. But then the question is, what is the critical value? The critical value we can only find out by looking at the table. So we have Z table, or what we call normal distribution table. I've shared the normal distribution table in Ulan X. Yeah. You can also Google for them. There are plenty of the Z table available that you can download, use. Now, be careful because different table, they may have a little bit of difference. So what would be the difference? Either the shaded area is on the left or on the right or in the center. So you must pay attention to the differences. So usually there'll be a note at the top how to use the table. Now in this case, you look at this case. In this case, they will give you the Z value. Okay, they'll give you Z value along the first column. Okay, and then the significance will be the value, will be the values in the rest of the table cells, right? And the Z here, yeah, here Z here is from 0 to Z. 0 to Z. So it's only covering the right side of the chart. All right. So whatever value given here is showing the right side. But what about the left-hand side? The left-hand side, as we know, is another half, right? 0.5. It's another half. So here on the left-hand side, 0.5, and then on the right-hand side is another 0.5. 1.48. So how do I use this table? I will look at 1.4 and then 0.08, you see? Because 1.4 plus 0.08, you get 1.48, right? So I'll be looking at the intersection. Therefore, if I ask you, what is the area, the green shaded area? The answer is 0.43056. But that's not the right answer. Yeah, I need to plus 5. So I need to take 0.4305 plus 0.5, which will give me 0.93056. Why? Because we want to get the all the value here up to 1.48 just now. Yeah, not just the right side of the mean, but also the negative side of the mean. We know this negative side of the mean is 0.5, right? So that will give us the correct one. Okay, 0.93056. Now, on the right hand side here is another similar table, just to show you. Actually, that in this table, it's giving you the area to the right. That's why I ask you to be careful when you're using the Z table or a normal table, name for its normal table. You must look at the notation at the top. Either the value inside the table is referring to the right hand side or the left hand side. Like the first table here is left hand side, whereas the one on the right here is on the right hand side. Now let's find out. Yeah, I want to find the Z value. I want to find the significance of Z value 0. Of Z value 0, right? So what I'm looking for is, you look at this side, Z. So I'm looking for Z 0. And Z0 means we take this one, 0.00, not 0.01. And then the answer I want is 0.5, which means that it's taking this whole part. Yeah, it's taking this whole part. Now, let me try another one. This time, I'm wondering 1.0. Okay, 1.0 is where? 1.0 is here, right? So if I find the value, this kind of table is only on the right hand side. So I'm looking at the shape on the right hand side. Okay, so 1.0 means, okay, the top here I take 0. That means I'm taking 0.1587. Yeah, so it's getting smaller and smaller and smaller. The more I go to the right, the area under the chart is getting smaller and smaller and smaller. See? That's why the value is getting smaller. Yeah. On the yeah. On the other hand, the table on the left hand side, because we are looking at the value starting from the mean. Yeah. So it's starting from mean. So starting from 0, of course, the value is 0. But if you go all the way to the right hand side, it becomes bigger and bigger. You see, 0.49. Eventually it becomes 0.5. Because it's the other half of the table. All right. So I hope you get the idea what I'm trying to say. Sorry for the hiccups, because my stylus and mouse is giving me a lot of problem. I'm not sure what is it. Cannot draw properly. The other table that you can use is percentage points of the normal distribution. Some books will have this page. So why I want to mention this is, you look at here, the objective is the same. The area underneath the chart given by alpha or significance, and then the z value, yeah, the z value which is along the x-axis, which determine the lower bound and upper bound of a proportion. So what is different of this table compared to the previous one is that instead of looking for the z, yeah, we start with the alpha. Just now we were looking at the z to search alpha, use z to search alpha, but this one is using alpha to search the z. Yeah. So what is alpha here representing on the graph? The alpha here is representing the area, the shaded area, starting from the right hand side, starting from the right tail of the curve. Yeah. So again, I have to remind you, depending on the table that you're using, it can be the shade can be coming from the left or from the right. Yeah. So you have to pay attention to that. Different books, they may have different convention. So those are some of the basics that I would like to highlight before we move on the proportion, because we'll be visiting those basics again and again in the calculation. Now, the head P. Sorry about this sign. You should look like this. The headed P that you see in the formula is called point estimate. Point estimate. Yeah. It refers to the proportion. So because its proportion is from 0% to 100%, but usually we just use 0, 0.1, 0.2, 0.3 up to 1.0. Yeah. So if 0.5 means 50% of the sample. If 0.75 means 75% of the sample. To come out with the point estimate or sample proportion, the formula is as follows. We take the number of occurrence divided by the total. Like just now, if you want to know how many survivals from the Titanic tragedy, so what we do is we are looking at the number of survivors and the total number of passengers. That will give us the point estimate for the survivals, the proportion of the survivals. Then you'll be wondering, hey, I already get 50% already, right? So why I need to go on with the rest of the steps? Isn't 50% already the proportion? The answer is no, because we are that proportion, the 50% is just the proportion of the sample. Remember, sample is not final. Sample is not accurate yet. Yeah, we want the population proportion, not the sample proportion, but we only have sample proportion. So how do we know the sample proportion that we get is correct or not? That is why we need to continue with other steps. Yeah? It's not just like, oh, I figure out x divided by n, that is the proportion. No, it's not like that. Yeah. So we need to have one assumption when we use a sampling distribution to determine the proportion. We need to assume that it is normal. It's based on a normal distribution. Now, some of the criteria that we can use to give us confidence that we should use normal is the sample size. As I mentioned, 30 and above is indicated that it's going to be normal. Yeah, and then for proportion, you have a further metrics that you can use. Yeah, you take the number, multiply by the point estimate. If it's greater than 10, yes, it is normal. Or you can take n multiply with 1 minus p. So n is the total number of sample. Yeah, and then p is the percentage of the sample proportion. Sample mean. So not mean, sample proportion. Okay, and again, it has to be 10 or more. And then additional thing, if you want to figure out the sample mean, you can use the p. Okay, you want to figure out the standard deviation, the sample proportion, then you can use this formula. Okay. So a confidence interval is a range of values within which the population proportion is expected to lie. So graphically, what is CI? If you go back to the previous drawing, CI will be the area between the lower bound and the upper bound. Okay, the area between lower bound and the upper bound. Now the formula will be the mean of the proportion plus minus the z value, the critical value. Remember just now I mentioned about critical value. So this is where you understand critical value is important. Okay, plus minus critical value multiply with the square root of point estimate multiply with 1 minus point estimate divided by the total number of the sample. Okay, so the critical value z, how do you know? Again, we get it from the table, like the one I showed just now. You can either use any z table you find, but make sure you read up the note first, because sometimes the area is on the right, sometimes the area on the left. Yeah, and sometimes it starts from the center, sometimes it starts from the tail. Yeah, you have to be careful. And then or you can use this table. It's the same. Yeah, the only thing that is different is the position. The previous one, you start with z to find out the alpha, but the second table here, the third table here, you start with alpha to find the z. Yeah, so you can use it complementary, not complementary lah, in alternative one another, because both of them serve more or less the same function. Okay, and then that will give us the interval. Now, if you look at this formula, right, why they use plus minus? You see why they use plus minus? Again, it has to do with this chart. So if you understand this chart, you'll be okay. So you see the chart, where is the center of the distribution? The center of distribution is the mean of the proportion given by the value 0. And then the standard deviation is plus minus to the right and left. The standard deviation is plus minus to the right and left. So you look at the formula, standard deviation, somewhat like standard deviation, yeah. This part of the formula, yeah, somewhat like the standard deviation. So you have to rely on the formula lah. You're using it to determine proportion. Make sure you use the right formula. You're using it to determine the statistical mean of a normal. That would be a different formula. So, for example, I want to know the Z from standard normal distribution or Z table, yeah, for 95% confidence. For 95% confidence. So 95% confidence, let us look at this table. Okay, 0. Okay, this was up to 38% only. See if I have 5. 95% confidence is 1.96. Let me see the table that we have, whether it's sufficient or not to determine this. You see this table, the standard normal distribution, right? And then here it says it represents left of the Z score. Left of the Z score, which means if I have a normal distribution like this, a normal means the center here is 0. Okay. Then every time I refer to the table, it will give me the significance value will be on the left hand side, not on the right hand side. It will be the left hand side. So let's say I look Z 0.3, because the x-axis is Z, right? Then the alpha value will be this whole area. Okay, because it says to the left. to the left of the z-score. Okay. What is the z-score? Z-score is the value at the along the x-axis. So it says to the left. Now this is a z-score. One 1.96, 95% confidence. 95% confidence. 95% confidence. So 95% confidence. 0.6. 95% confidence. Okay. Hypothesis testing for population proportion. So to answer some of the problems in the assignment, they're basically all hypotheses. You want to, as you have tried earlier problems, all of the questions are hypotheses. Whether you're determining the mean or the proportion is all hypothesis. So the null hypothesis is the assumption that no difference or assumption that it is equal. Assumption that's equal or no difference. That is usually the null hypothesis. The alternative hypothesis will be there is a difference observed between the population. Okay, so the general steps for testing the hypothesis of population proportion. Yeah, number one is to come up with a null hypothesis that the if it's one population, then you'll be comparing that population with the normal population. If it's two population, then you'll be comparing population 1 and population 2. If you have more than two population, like population 1, 2, 3, 4, 5, then the null hypothesis is that population 1, population 2, population 3, population 4, and 5, the proportion are all the same. The alternative hypothesis is one of the proportion is different. So that's how you state the hypothesis. And then choose the significance level. Usually we choose 5%. Yeah. Usually we choose 5%. You want to be stricter, then you choose 1%, because 1% gives you more confidence, because the confidence is given by 1 minus 1%, 99%. If you use 0.05, the confidence is 95%. Right? So you choose 5% or smaller is good enough. And then for proportion, for mean, there will be different formula. For proportion, the formula that you can use will be like this. Z, yeah, the Z of the sample that we want to compare with the critical value. Remember just now the critical Z is coming from the table, right? That one is given from the table. But we want to calculate our Z and then compare our Z with the given Z. So how to calculate our Z? We use this formula. You see this point estimate? This point estimate is given in the question. And then P0, okay, divided by P0, 1 minus P0, divided by N. Okay. So the P0 is the standard, proportion. The standard proportion from the population. Remember, there are two things we are talking about here. This is the part where it may be a bit confusing. Let me write it down. Sample, sorry. Okay, where's my stylus? I want to write. Okay. Uh, Sample proportion. And then the other one is population proportion. Sample proportion refers to one. And then the population proportion is P0. So what is N? N is the sample, not the population, the sample size. Yeah. So you must be careful with the word sample and proportion. Two different things. Sample sample is let's say this is the population. Sample is the subset. The question is the subset good enough to represent the population? Is the subset proportion good enough? Is the samples proportion good enough to represent the population proportion? That's why we are doing all these things. Yeah. So once you get a Z, right? Once you get this value Z, what do we do with it? So we go to the table. We go to the table. What table? Table like this. Okay, you see on the table here? All these are Z. All these are Z. Okay. Now for this table, it's the balik. It's the other way around. You see all the Z here, all the Z is in the center, and then we figure out the alpha on the first column. Then we take the critical value. We use the Z to find out the critical value. Okay, and then this is coming from the table, and then we compare our Z with the critical Z. Our Z versus critical Z. Forget about it. Okay, where critical Z comes from the table and Z is calculated one based on our formula. This is the calculated Z and the other Z from the table. So the steps are similar, almost similar for one population, two population, or more than three populations. Just now, the example we have seen, the general step we have seen is actually for one population. For the two population, there's a slight difference in the Z formula that we use. Okay. And then for the more than 2 population, again, the difference is on the formula we use. The other steps are the same. So if you look at it, one population, hypothesis, determine the Z, find the critical Z, then decide whether to reject or not. If the calculated Z is bigger than the critical Z, reject the hypothesis. All right. Same goes for 2 population. You see, hypothesis first, then determine the Z. What is different? The formula to get the Z. And then find the critical Z. Okay, finding the critical Z, the step is similar with some slight difference, because note that the significance will be divided by 2. Because for 2 population, we divide by 2. You see where my mouse is pointing? Yeah. The critical Z is determined by using significance divided by 2. Okay. So I think we will look at examples to understand this. Then more than 2 population, we will use this formula, chi-square. This is a Greek letter called chi. Chi-square, which is coming from the differences between observed value with the expected value square and then divided by expected value. I think again, this understanding will come by looking at examples, which I try to find time later on to show step by step. Okay, and then again, similarly, if the chi-square that we calculate is bigger than the chi-square that we get from the table book, we reject the hypothesis. Okay. So there are some key formulas. You have seen what sample proportion is. Sample proportion is to determine the point estimate. And then you have I have also talked about the confidence interval, which is the lower bound and the upper bound in the normal curve. You can determine them by using this formula. And then to determine the Z, to determine the calculated Z, we use different formula for 1 proportion, 2 proportion, and more than 2 proportion. So in the assignment, I have posted same questions. Example 1, okay, this is in your assignment actually. A sample of 100 passengers shows that 60 survive. Now, is this looking for mean? No, it's looking for fraction, right? Fraction, aka proportion. We want to know, is it true that 60% survive? Yeah, 60% survive. That's whether the population proportion of the survivor is 0.5 at a 5% significant level. Wait, doesn't this look funny? You see, this is 50%. But the formula, but the value data given here is from the sample. Actually, the number of passengers is not 100, no? Many, yeah? Many, but we're just saying 100 passengers, 60 survive. This is the sample proportion. Sample proportion, 60%, 0.6. The 0.5 here is not sample proportion, but population proportion. And then the alpha value is 5%. Alpha value is 5%. And then what do we do first? We come up with a hypothesis. So since this is 1 population, we will be comparing this population with the standard population. Okay, with the normal population. Okay, which is there any difference between this sample population, sample proportion with the population proportion? Sample versus population proportion. That's what we are comparing. So null hypothesis says same. Null hypothesis always say same, no difference. Null hypothesis is always like that. Yeah, you don't say now in null hypothesis that there is a difference. The answer is no difference. Any null hypothesis like that. And then you get the value of Z. So how do you get the value of Z? You need the P estimate, right? Point estimate, which is 60%, 0.6. And then this P0 is what? This is the population proportion coming from 0.5. So you just plug in 0.5, and then what is n? N is the sample size. What is the sample size? 100. Yeah. So by doing this, you will get the calculated Z. We compare this calculated Z with the critical Z later. Now, how do we get the critical Z? You use the calculated Z, refer in the buku sifil, refer in the table in order to get the critical Z. Then you use your calculated Z, compare it with the critical Z. Your calculated Z, if it's bigger than the critical Z, you reject the hypothesis. Okay, so I just explain the question first, example first. Then later I see how much time we have, and I do I show example how to come up with a solution. And then example two. Let's understand the question first. Compare the survival proportions. The keyword is compare. Compare what? Comparing mean? No, compare proportions. Compare proportions of males and female. So there are two proportions. There are two groups here. Yeah, there are two groups here. Okay. One is male. The other one is female. For the male, out of 50 males, 20 survived, 30 died. Out of female, female, about 50. You see, this is a sample, not the actual population, because the actual Titanic passenger is more than 50, right? Because we are just doing sampling. Out of 50 that we have in our data, 40 survived, 10 died. Wow, survivability for women are higher, right? If you look at this data, test at a 5% significant level. So what do I mean? Test what? Test the proportion between male and female. Is there a difference or not? Maybe the proportion is the same. The number of proportion is the same. So you'll be wondering, obviously here male 40% survive, female 80% lah, because you see male is 20 out of 50, female is 40 out of 50, right? But wait, this is just proportion for the sample, not the proportion for the population. We want to test whether it is true or not at the population level. The male-female, the proportion is similar with confidence 95%. Yeah, 5% significant level means confidence 95%. So what do we do? Again, form the hypothesis and then find the Z value. So the Z value here, you have a sample proportion for male minus sample proportion for female, and then you use this formula, you know. Just plug in the value, you know. Okay, N1 is the size of the male, 50, and then N2 is the size of female, also 50. Then you get the calculated Z. Again, you need to do two kinds of Z. One is the calculated Z that you use formula, and then the other one is the critical Z that you refer to the table. So you use a calculated Z to figure out the critical Z in the table. And then if the calculated Z is bigger than the hypotenuse, so it's bigger than the critical Z, you can reject the hypothesis, say that no, they're not the same, proportion is different. So hypothesis is quite limited. Hypothesis testing, you can only say you can only prove that the hypothesis is correct or fail to prove that it is correct. And then the third example, let's look at it. What is it looking for? It asks you to do chi-square. So it already gives you the formula. It asks you to use this formula, chi-square, to compare the survival proportions across 3 passenger classes. You see, the keyword is proportion, and then here 3 passenger classes, not 2. So it means you cannot use the previous formula. This is for two classes. This one is for 3 classes. So you see, you use different formula, and this formula requires you to draw the table. Yep. To draw the table, estimation table, for you to figure out the values that you can plug into this in order to come up with the chi-square value. So again, you have 3 classes, class 1, class 2, class 3. Class 1, 50 passengers, 30 survive. Class 2, 100 passengers, 60 survive. Class 3, 150 passengers, 90 survive. So first class, obviously the number of passengers who can afford first class will be few lah, 50. Whereas the third class is the cheapest. That's why there are more people in the third class. But the interesting part that we want to study is the survival proportion, to see whether they are safe. Like when people die in Titanic, there's no difference between whether you're first class, second class, or third class. You want to see whether that hypothesis is true or not. Or actually there are differences. So we want to test whether it is similar. If it is not similar, what could be the factors? We wouldn't know. The factors we have to find out other way. Statistics only tell us whether there's a difference or not. So we will go into the examples step by step later on. Yeah, I want to finish up the slide. Key points. Today we are learning about population proportion, not means. So what is proportion? Fraction of the total for certain characteristic. Depends what you're searching for. And then for proportion, we need to refer to a distribution. So we have sampling distribution and population distribution. Normally, we go for normal distribution. Normal distribution for both sampling and population. Confidence interval is the range for the population's proportion. So what is the boundary that separate this group from another group? And then hypothesis testing is used to test claims about proportions. And there'll be different formula for one proportion, two proportions, and more than two proportions. For more than two proportions, we will use chi-square test. So yeah, that's about it for the for chapter for module 3 on proportions.